Ladies and gentlemen, welcome to the channel of Beyond Consultancy, where we discuss all things operations excellence. My name is Herman Lemmens. In this keynote, we will explain the economic production quantity. This keynote is the fourth of a series. In the previous keynotes, we discussed the economic order quantity. If you are new to this subject, you may want to take a look at them first. Let us proceed with this keynote. To quickly recap, the economic order quantity model determines the order size at which the sum of the total inventory and ordering costs is minimal. It assumes, amongst other things, that the order is delivered in one single batch. If instead the order is delivered incrementally, then the economic production quantity model determines the optimal lot size. This situation is applicable to the production shop floor. Note that the economic order quantity ordering costs are in fact replaced by the setup costs. The EPQ is also known as the EMQ for manufacturing or the EBQ for batch. The model was developed by E.W. Taft in 1918. Let us put one thing and another into a value stream map. The production planning gives the process A an instruction to produce the optimal amount EPQ. The process A runs at the rate P, for instance 100 units per hour, and delivers these units into the work-in-process buffer of the receiving process B. This process consumes the units at the rate D, which must be lower than P, for instance 40 units per hour. This diagram illustrates the basic setup of the economic production quantity model. However, with the example numbers, process A would have about 60 units per hour idle capacity, so we could do this. If the situation would allow for it, we could have process A switching between supplying B and supplying C. This diagram suggests the wider possibilities of the EPQ. But let us detail the model first. This time diagram depicts the evolution of the number of units in the work-in-process buffer of the receiving process. On average, there will always be a number of units of safety stock available in the buffer. Assuming a production rate P, between production start and stop, Q units are produced. These units are drawn out as they arrive. If the takeout rate is D, the WIP will only grow at the net rate of P minus D. By the time the production stops, the WIP reaches a value of safety stock plus I max. In order to determine the inventory costs, we need to find out the average inventory size. In a similar manner as for the EOQ method, in situations with a linear inventory profile, the average inventory is given by the maximum value divided by 2. Hence, the total inventory costs for the period equal the inventory cost per unit H times the average inventory size, which is I max divided by 2. I max is a fraction, P minus D divided by P, of the total quantities Q. We can rewrite this formula into a more simple form and substitute it into the inventory formula. We now have the total inventory costs in function of Q. To this, we now need to add the total setup costs during the period. This is the same formula as the ordering costs in the economic order quantity. Together they determine the total cost function for the economic production quantity model. To solve this equation for Q, we could follow the same method as in the EOQ model, namely to take the first derivative, equal it to 0 and solve for Q. We can also take a different path. Indeed, we remember from the EOQ analysis that in the optimum point the inventory costs equal the setup costs, so we can straight away write this formula. We now multiply both terms with Q and transfer the factors to the other side of the equal sign, and come to this equation for Q square. Taking the square root, we come to the final formula for the economic production quantity. On the following pages, we will further analyze this formula. A first analysis is graphical. We start from the economic order quantity graph. The total cost function is shown by the red curve. It is the sum of the yellow line, which stands for the total inventory costs, and the orange line, which stands for the total ordering costs. Assuming the same values for D, S, and H, we can superimpose the economic production quantity curve. The EPQ and the EOQ have the same ordering or setup curve. The EPQ has a lower inventory curve, and thus the optimal lot size in the EPQ is larger than the EOQ. As we learned from the graphic analysis, for the same D, H, and S, the economic production quantity is greater than the economic order quantity. If P is much larger than D, then the inventory builds up faster and the EPQ approaches EOQ. If, on the other hand, P only slightly exceeds D, then the inventory remains very low and EPQ becomes large. It begins to represent a continuous production flow. Note that the rate P should always be strictly greater than D, otherwise the formula crashes due to a division by zero or a negative square root. In the real world, this corresponds with negative inventories. This brings us to the close of this keynote. Thank you for being here. I hope you found it interesting. Please leave your views in the comment section below, and I hope to see you again.